We are moving on to Srinivas. He's received his PhD in electrical and computer engineering from the University of Illinois at Urbana-Champaign in 2007, after which he was a postdoctoral scholar in management science and engineering at Stanford. He joined Texas A&M University in 2008, where he's currently a professor at the Department of Electrical and Computer Engineering and at the Department of Computer Science and Engineering by courtesy. So welcome, we appreciate you, and the clicker's right here. All right.
Thank you so much.
You're really welcome.
Thank you all for being here on the very last day, last session. So this talk is a joint work between Texas A&M primarily and UC San Diego, although we're reaching out and we have more and more users and a lot of fun stuff happening with EdgeRIC. So EdgeRIC is a platform and also a project in which we are developing a variety of algorithmic kind of contributions. And our focus has been on real time. So without more ado, several of our students are also here. Ushasi is here, Ali is around, I've seen Woo-Hyun, a whole bunch of our students from our group are around. So this is really the group working on EdgeRIC, both at Texas A&M and UC San Diego. And as I said, we have already started collaborative activities with NCSU as well at this point. So what is the point and what are we trying to do? If you look at the next generation of applications, I think that really doesn't need motivation for this group. Really a lot of them are dependent on quick access to edge compute. Like for example, in this case, I work with an autonomy group, for example, at A&M, and they're interested in situational awareness. In other words, you have to sense, communicate, get a situational awareness map, send it back to the vehicle. It has to happen in time for you to basically not kill pedestrians or avoid the other cars. So in other words, the latency and the end-to-end latency for many of these applications are of the order of 20-ish milliseconds. You have to be able to get there and brake in the right time. There are even more kind of critical applications, time-critical applications. Like for example, when you look at AR, VR, and real-time gaming, if you look at VR, right, what is critical there is so-called motion to photon latency. You move your head, you need a new frame in front of your face. This has to happen, if you're looking at 60 frames per second, this has to happen within 16 milliseconds. If you basically want to do higher 100 frames per second, which is considered very good, it has to be 10 milliseconds or less. So you have to do everything in that period. Your head position has to go to the edge, it has to render the frame has to come back, display 10 milliseconds or less. Right? If you do 120 frames per second, it is 8 milliseconds. In gaming, similarly, you have to make sure that you have to know who killed whom and these kinds of things. So real-time applications are kind of the coming thing. And they're all dependent on sub-millisecond or sub-10 millisecond access to the compute, which means the actual comms has to satisfy a few millisecond stops, because you're doing a bunch of compute at the edge as well. So that is the nature of the beast in terms of applications that we need to support. Now, if you look at the cellular networks, they are becoming more intelligent. And the idea is basically that RAN Intelligent Controller, RIC, is the seat of this intelligence. It's a disaggregated element which would host essentially the algorithms and applications which are used to manage and control this. So that is the nature of this connectivity. So now, of course, everybody here has heard the term and you're familiar with a variety of RICs. Now, the question is, what is the issue with the current near real-time and non-real-time RIC? The issue is it is not real-time. So why is that critical? If you look at the front hall, you've got the radio sitting there as well as a little bit of edge compute, which is at the DU level. All the stuff happening there is at hundreds of microsecond type latency, right? The actual transmit time interval in a system, in 4G it might be 1 millisecond, 500 microsecond. In 5G you can bring it down to 250 microsecond, even 125 microsecond. So in other words, the transmit time intervals are very small and are within this front hall area. The channel conditions change at that frequency or that periodicity as well. So if you look at mobility scenarios, you're walking around, channel is nice and stable. You're starting to move in a vehicle, it starts getting more unstable. The Doppler is starting to hit you. You're in a fast moving vehicle, you're seeing sub-millisecond type of changes. Now, how are you going to deal with sub-millisecond type of changes if your seat of your intelligence is 10 to 30 milliseconds away? So that is a critical aspect. So in other words, the existing RIC topologies and approaches, can they deal with essentially real-time problems, right? And now you're going to do FR2, millimeter wave is even worse, FR3 is somewhere in between. So in other words, you really need to have some kind of real-time adaptivity. You need to be able to access your KPIs from your network in real time, control it in real time, right, at this transmit time interval. So this is not just made up. We have a facility at Texas A&M. It's a former Air Force base where we can go and try out various things. We have flown drones, we drove cars, etc., to gather CQI, channel quality data, and that is actually a drone trace. If you look at the CDF there, the change duration of the CQI, that's basically more than 60% of the samples, that's the leftmost graph, are less than about 5 milliseconds. So in other words, So basically this is a very real thing. Channels do change at sub 10 milliseconds, definitely sub 5, even a few 2-3 millisecond time scales. So you don't have the luxury of doing your scheduling or whatever you wish to do at near real time, and definitely not non-real time. So the other issue is that networks typically are completely application agnostic. This is true of the internet itself, in that until layer 3, it doesn't care what's underneath, what is actually being hosted. Now the problem with that is, if you're looking at these new age applications which are super demanding, like for example they want really quick access to edge server, well, if you don't know about what the application desires, you can't deal with it. Say for example you have a video stream or this AR VR, and you need a frame, you need it now, you cannot delay, right? So specifically if you're looking at a video stream, if your buffer is run dry, the individual is going to see a circling screen, and that is going to be deadly in the case of the XR type of application, because people get nauseous, specifically if there are delays and the screen the visual drags past the head motion. Then you feel really dizzy because you feel that you're not really positioned in space correctly. So these are real issues in terms of, if you don't have awareness of what the application desires, how are you going to support it? So basically, can we incorporate application awareness at a fundamental level into the RAN stack? So of course, what we should do is somehow provide a side channel wherein an application, if it so desires, can actually provide you such information, and then you can prioritize as appropriate. So this is really where EdgeRIC is coming from. The idea is, there's the DU over there and CU and the core up in the cloud with more than 10 millisecond latency. What we want to do is connect to the RAN stack at the DU level with essentially sub-millisecond latencies, right? We want to extract KPIs from the RAN stack. Right now what we're doing is we are able to extract them at about 30 microsecond or less, right? Then we process it. You have to run your algorithm, whatever you are running on EdgeRIC, and it has to send stuff back within that same round trip time. And we typically are trying to achieve at least 125 to 200 microsecond round trip times. Of course, side info is available also from the application. So application, for example, this business of video buffer that I mentioned, if your app wishes to provide video buffer info, you can get it. And so you can use it as side info. So essentially what we're doing is application aware and real-time schedule, real-time kind of access to KPIs and control, so that you can do unprecedented low-level 5MAC related optimizations. So that's our goal. Can we actually do this? So here is actually our messaging scheme, which basically shows that as you scale the number of UEs, typically the round trip time is bounded within 100 microseconds. So yes, you can actually do it. We actually also do a TTI by TTI sync. In other words, the RAN tells you which TTI its KPIs belong to. The RIC knows that and can say, okay, apply what I'm saying to the next TTI or a few TTIs down as needed. So you can go back and forth, RAN, RIC, synchronized at every TTI. So that is the nature of the thing, that we can actually achieve this with EdgeRIC. Now, the real-time system platform, of course, has the core and RAN as usual. This is built on srsRAN. We have just recently also integrated with OAI, but the implementation, which is up on the web, is srsRAN with 4G, and hopefully in the next day or so, we'll have the 5G version also out. So this is the typical or traditional scenario, wherein the RIC which you have is near real-time, non-real-time, which is up in the cloud. So to that, we add EdgeRIC, which is a real-time RIC, right, connected at the DU level. And furthermore, they can share info. You can basically, in fact, we've shown this hierarchical usage of multiple RICs. You can basically share info with the near real-time RIC. So for example, if you want to do machine learning training, you want to share data with it, you want to have high-level policies, it can share it with the near real-time RIC, and EdgeRIC can pick it up and use it. In fact, some of our demos, you can actually see the ML models which are being trained in a near real-time or non-real-time situation being dropped into the Redis database, which is that blue box in the middle, and pulled from EdgeRIC so that it can grab them and use them, right? And you can see in runtime, you can do this. This disaggregated architecture facilitates that. If EdgeRIC were sitting inside the RAN stack, you would break things because timing is critical in the RAN stack. You have to do what you got to do. So if you sit there updating models and whatnot, you might break the RAN stack. So our fundamental watchword was you cannot break any of the critical time elements in the RAN stack. So we embed an EdgeRIC agent in the RAN stack, very much like an E2 agent, but all our processing related to EdgeRIC and whatnot are outside the RAN stack. It is disaggregated from that perspective. And we basically run these things called micro apps, these little things, mu app 1, mu app 2 down there. So micro app refers to the fact it needs to run with microsecond latencies. Right, and I'll show you a few of them and how fast they can run. So our platform is application aware in that it can get side info from applications. It is basically it can handle dynamic environmental changes because it is operating with sub-millisecond latency. Channel changes it can deal with, right? And finally, it is largely ORAN-like. There are a few changes we had to make to the E2 standard in order to allow for this real time, but it's philosophically almost identical. So you could argue that it is somewhat like the E2 interface, except it's been modified to make it real time, and EdgeRIC has this micro apps kind of platform on which you can run. Incidentally, the whole thing is open source. You can download it. Shashi is going to give you a tutorial. We did a workshop on it last month. You can run it. It works, right? So do we need it? Is it worth using? First thing is regarding this real time. So if you look at the left side, you see the throughput on EdgeRIC, and in the middle is basically the throughput on a near real time, 30 millisecond latency. So this is with a flaky channel. You notice the throughput is dramatically different. It's almost 10 Mbps different, simply because if you're doing a scheduling algorithm, this makes sense. If you may do a scheduling algorithm in which you don't know what the channel is, or you know the channel as it was 30 milliseconds back, it's not going to work very well, and that's essentially what we demonstrate. More interestingly, if you try to do machine learning specifically, so my background is on optimization and control really, and so what we were very interested in is looking at the system as a feedback control system to do reinforcement learning. We want to do scheduling. I'll come to that in a bit. But when you try to do ML training in these kinds of feedback loops, what really hurts it is jittery delay. So in other words, for those of you familiar with reinforcement learning, there's a notion of state. Then you do an action. It results in a next state and a reward, a performance basically. Now, if there is this correlation breaks, I did something and something happened, as that correlation breaks, the system fails to train properly. And you can see that on the right side. So the left side is EdgeRIC and the right side is near real-time RIC. It's quite haphazard. It never actually trains very well, right? It's okay if the delay is pretty much deterministic. If you can guarantee 10, 15 millisecond delay bang on target, then you might be able to train reasonably. But if it starts jittering around, it makes this correlation go haywire, and it doesn't train very well. And then if you do manage to train good policies, what's the value? You notice here, this is an application-aware example. Essentially what it's showing is the stall condition, stall probability. Small is better, basically. The fraction of stalls which happen when you have EdgeRIC, which has the application awareness, versus an agnostic scheduler, which is just doing what it does. You notice the stall probabilities are dramatically lowered. So knowing what your application is up to is actually useful, right? So I wanted to spend a little time on EdgeRIC's key features, then I'll show you a few videos. So first of all, it is real time. That is fundamental. It accesses the RAN stack at TTI timescale and does what it does. It has application state awareness. Side info from apps are available. And it has the shared database, which I mentioned, Redis, where things can be dropped from other RICs. And that comes to the ease of deployment, which is the way we write our apps are basically you just take EdgeRIC library, write your Python code, drop it in EdgeRIC, it'll run. So all you have to do is use the right APIs to collect what you want and write your algorithm. The last one is we also developed an emulator mode for it so that you can train machine learning algorithms without any radios. You can just run it on a workstation. So all in all, we're going to show you several examples of these micro apps and with real-time AI in the loop. We've been working on this for close to 2 years at this point, year and a half plus, and now our publications are all coming out. So the main EdgeRIC paper was at NSDI this year, right? Earlier we had posters, we had demos at SIGCOM and so on. So and now there's a hot mobile paper on beam management with it, and now we have a CONEX paper on essentially multi-RAN site resource allocation with it. So a variety of papers with different use cases are coming out. So I'm going to show you a few of them. So first one I'm showing you is RL-based scheduling. RL is reinforcement learning. Goal is I see the system, the physical environment, as an environment, and I want to do a feedback control scheme for scheduling, PRB allocation. So in other words, I'm going to pull the channel state info and the queue length info from the RAN. The RIC is going to decide who gets what PRBs, and the value proposition or the reward function here is throughput. So how do we do that? So this is what we're doing. It's at EdgeRIC. It's got this disaggregated system. So we see essentially this the world, the environment, the RAN system as basically as the environment. You notice that yellow box in there, that is the EdgeRIC agent, which is philosophically very similar to an E2 agent. It basically grabs stuff from the RAN and sends it over to the RIC. So besides that, we have a database. It's essentially a Redis database, which allows us to collect KPIs and send it to wherever, in this case to a near real-time RIC for ML model training. Now this model is nicely trained. You drop it into EdgeRIC. EdgeRIC will run in real time. So that's the notion. So we want to leverage the RL for these RAN optimizations. So the important thing as far as RL is concerned is practically all the code bases. You go to Hugging Face, for example, all the code bases are OpenAI GYM compliant. So we have to see the world as a GYM class environment. And so that's really how the EdgeRIC sees the world. So all these micro apps assume that there is a GYM class environment. And so you put your favorite Hugging Face code in there, it'll run. And so once you do that, the RAN will, of course, do RB allocation in real time, proportional to the weights received from EdgeRIC. So that's the idea. And the point is, we can therefore do QoS, QoE optimization with real-time telemetry. So in order to train, I mentioned that up there, in the blue box up there, is where we do our ML training. We can train in the real world, but that's usually not super attractive, because one, you have to run the system a while, and your users might get unhappy with you in the meantime. And two, it basically, you may want to fine tune rather than train the original model from scratch. So what we do typically is we train our base model outside in a simulator or an emulator, which is what TinyTwin is. So we want to train the base model, and then we can fine tune in the real world. So in order to train our base models, we use the exact same stack, except we don't have a radio. So on the left side is the usual RAN stack, right? And then we have a whole bunch of UEs. This is srsUE actually. We couple them with GNU radio, and we also collected a whole bunch of channel traces, right? So we can stick them into the GNU radio block in order to basically play back the channels. So you can do end-to-end applications, train the ML algorithm on EdgeRIC, but you're using the channels collected from wherever. So this gives you actually a nicely trained model, which oftentimes it just works. The vanilla model you train from this will work in the real world. If need be, you might need to do some fine-tuning in the real world. So this is what I said about collecting channel traces. We've been doing that for a while now, and we'd like to continue doing that for a variety of cases. Occlusion, fog, these kinds of things are all interesting physical environmental conditions, different frequency bands and so on, so that we can actually use it. Now, here is our first EdgeRIC video. This is on scheduling. So what is going on here is we have an srsRAN base station, 2 srsUEs there. So it'll show up in a little while. Yes, this is with, I think, a 10 megahertz channel. And what the idea here is to do downlink scheduling. What you'll see is in real time, what is the impact of using different schedulers. And the scheduler is being updated in runtime. So this is a max weight scheduler, which is basically giving a certain throughput. The next thing we're going to do is swap it out with a 50-50. Each one is absolutely fair. It drops the throughput a bit. And then you use an RL-based scheduler. So there is the throughput which has fallen because it's a partially trained model. So that's going on. And now you drop a new model in there, the throughput improves. Now you're going to drop another model, and the throughput will jump even more. So there's our the third model, and there it is. So essentially what's going on therefore is that as the models are updated, you can basically adapt to the current situation. That current situation, we have tried things like you put a little piece of metal in the between, it'll adapt to that, for example. So in other words, as you try to modify the channels, it will adapt to the situation. Now, one concern we had with all these RL trained models is basically that they're not super scalable. If I train, for example, in which 2 UEs want a URLLC, 5 UEs want EMBB, 6 UEs want XR, and now I want to run it in a situation where the situation is different. How am I going to scale to that? Because I can't train an RL model for every situation on the planet. So one critical angle is how do we scale, right? And so we've come up with a policy, which is called a Windex, it's called, in which we can encapsulate the actual state of each UE, how many backlog packets it has, its channel quality, and how well we are attaining its targets into a single number, which we call its index. It's a so-called Whittle index. And then we can prioritize based on that. In other words, supposing I have a UE which was meant to do XR, it's got a pretty decent throughput guarantee. It has not, its latency is looking good, its index will be low. On the other hand, if somebody who was promised an XR, its throughput is not so great and it's seeing latency, its index will be high. So using such index policies, we can actually schedule in a manner that is scalable. In the sense, on the left side, you see a big RL policy, which took about 200 microseconds to run. The index policies take only about 10 microseconds per UE, and you can parallelize them. So you can run them super quickly. So that shows basically it's 10 microseconds to run the policy. So once you have this, you can actually do priority-based scheduling. In this example, we have 3 UEs. The first scheduler out there is the max wait scheduler. Left side is throughput guarantee, right side is latency guarantee. Max wait is doing well on throughput. Small is good. So 0 is good. Anything high is bad. Max EQI does okay on throughput. It does horribly on latency. The Windex-based scheduler is the blue one. It's doing well on both throughput and latency. So that is the advantage. You can get basically maintain guarantees on a per UE basis in real time. So how will we use this kind of thing? You may have seen Wuhan's demo earlier today. So this is connected intelligence, where what we're trying to do is this robot out here is sending LiDAR and camera info, video info to the controller, who is sending the control signals back to the robot. Now what is happening out there, you see the throughput is relatively low, robot is doing fine, you can see this video moving along nicely. Now what Wuhan is going to do in just a second is he's going to load up the thing by sending a huge bunch of iPerf data. So it will jump suddenly. And when it jumps, the native scheduler, which is round robin, is going to start seeing kind of laggy behavior. In fact, it's been sped up a little, but if you see this demo in practice, as he moves the controller, nothing will happen. It lags a lot. So he's changing the scheduler once more to the RL-based scheduler. It'll happen in just a second. The throughput drops simply because now it's giving priority to the robot as opposed to the load, and now it's working fine again. So this is the kinds of things you can do. You can basically prioritize whom you need to, when you need to. So that's a big advantage with regard to maintaining service guarantees. So in this context, what we've been doing now EdgeRIC is a platform, it's available. So we can run a variety of ML algorithms. Specifically, the big thing today is language models, time series generation, time series prediction. What can we do with time series? You can get context. I can tell you if this is a flaky channel. I can tell you if this is occluded. I can tell you what kind of traffic is going on by looking at the arrival rates of packets. So in other words, what we can do now is look at time series and start gathering to find out what is the interference situation and control in real time. So really, this is what we're up to. We're looking at transformer and state space models, which can actually give you contextual info on how best to look after your system now, right? So we're doing things like channel prediction. I don't have a video on this. It's just about working nicely. So it basically determines what is the class of traffic by just looking at the packets coming in. It can be augmented by QoE feedback. Your app can say, I'm doing fine or I'm not doing fine. So basically with these two kinds of info, you don't need to classify, or the traffic doesn't have to tell you in advance what class it belongs to. It will just work, so to speak, right? And going forward, one thing I want to point out, of course, is these all have to run with millisecond or sub-millisecond latency. All our ML policies are we make sure they run with about 50 microsecond tops or 100 microsecond latencies. In general, finding context is a slower process. However, we found so far, even with GPU access and so on, we are able to train context networks with about 3 millisecond runtimes. In other words, I can get your context every 3 milliseconds, which is good enough for most things because you don't change your application. You change your application typically in seconds. Your situational context in terms of channel qualities or channel types are not going to change too frequently and so on. In other words, if you're in a car and you're driving at 60 miles an hour, you're going to be driving at 60 miles per hour 3 milliseconds from now, pretty much, right? So that's essentially the kind of context we're looking for. Well, and now we've just started thinking about, can we use multimodal language models? In other words, you look at logs, you look at the contextual info coming from the network, can you actually say something interesting? So we're just starting on that. Now I want to say that we aren't working only on the MAC layer. We're also started looking at physical layer, MIMO precoding. So this is a nice application with Ish, who is going to show it at the end of the tutorial, in which what you want to do is beam nulling for an interferer. So what's going on here is basically we are getting essentially the receive stream, essentially the vectors of IQ samples in this case. More recently, we are looking at other KPIs. And what you come back with is a MIMO precoding vector. Essentially, the goal of this is to determine which angle to null at. So if there's an interferer here and there's the actual UE there, you want to null in the direction of the interferer while increasing the signal strength of the UE. That's the kind of thing you can do. This is essentially how you choose the actual beam nulling. So you can see a video here. This is called beam armor. And so this is 2x2 MIMO on the end of the base station. And the UE is, of course, ISO. So what's going on here is we're looking at uplink. So there's the base station, and there's the UE, and the jammer, the interferer. So what's going on here is, therefore, the setup is the usual srsRAN. We're using 10 megahertz channels and 2x2 MIMO here, because 2RX, 2TX, 2RX. And we are looking at uplink. So the base station there is running SRS UE. This was with the 4G stack, actually. And again, it's doing 1 RX, 1 TX. So it's doing single, while this is doing MIMO. And then there's the interferer. So the jammer is basically a Pluto SDR, which is basically kind of jamming in 5 megahertz. So now the question is, how is it going to work? So essentially what we're seeing is the UE is going to transmit uplink. The IQ samples are gathered. The beam weights are chosen in real time. And the beam weights are periodically refreshed in order to nullify the effects of the interferer. So that's really what is going on. Now you'll see the demo. So initially, of course, you're trying to estimate these alphas. In other words, you're not actually, the UE is not transmitting. So you've got a kind of clean set of IQ samples. Now the interference is happening, and you see that the SINR is about 10 dB, right? And now when the beam armor is operational, it rises to another 10 dB. So in other words, you're getting 10 dB of SINR extra by virtue of nulling in the right direction. So essentially that difference there is 10 dB, and the throughput is almost double, really. So these are the kinds of fun stuff you can do if you have access to real-time KPIs as well as control. And that's really the whole point of EdgeRIC, right? And we'll see a tutorial now. Thank you very much.